Now we shall discuss a next type of projectile, which is a projectile that is fired from a height. Till now we have discussed a normal projectile which is fired from the ground and it comes back to the ground, or a projectile which is fired from a height but with a horizontal initial velocity. It was fired horizontally, right, initially. This time we are taking a more general scenario. So what we have here is a certain projectile which is kept already at some height, let's call it h, and from here now it's not projected horizontally but at an angle like this, so that when it falls down over to the ground it comes like this. And what all do we know about this projectile is its initial velocity u and the angle that it makes from the horizontal direction. So if this is the horizontal parallel to the horizontal plane, which we are calling as the x-axis, then this angle theta is also known to us. Okay, so in order to study this projectile, we can consider the point of projection, the point O, as the origin. So this point O has the coordinate 0, 0, taking the rightward direction, horizontal rightward, as along the x-axis, the positive x direction, and the vertically upward direction as the positive y direction, right? In this case, understand that as the projectile reaches the ground, this point, which we can call as, let's say, the point P, here the coordinates of this point, if we assume that, let's say, the projectile hits the ground at a distance r away from the foot of the position from it where it was projected, this r, we know, we have been working about this is called horizontal range of the projectile, right? So if this distance is r and the height from which the projectile is projected is h, considering the point O as the origin, understand that the coordinates of the point P then will be r comma minus h. The minus sign comes because we are moving down the vertical direction. We have moved, the projectile has finally moved down, right? And we have taken the upward direction positive. So these are the coordinates of this point, the final point where the projectile lands. Also understand that since this projectile is still moving in air all the time, the acceleration that it suffers is at any point in time g in the downward direction. So this is the acceleration along the y direction will be minus g, putting the minus sign corresponding to the downward direction, whereas the acceleration along the horizontal direction ax will be 0 because there is no force, no acceleration along the horizontal, right? So we understand that for this projectile also, since there is no acceleration along the x-axis, the velocity along the x-axis at any point in time will be the same as its initial velocity along the x-axis. And what is the initial velocity along the x-axis? If we look at this from the figure here, dropping a perpendicular and trying to get this value, this length will come out to be nothing but u cos theta, the usual x directional initial velocity, u cos theta, right? Whereas the initial vertical velocity uy will be u sin theta, right? So ux, the initial horizontal velocity, is not going to change as the projectile proceeds and reaches the point P. So in order to study this projectile further, we can once again use the same basics. We know that ux, which is u cos theta, and uy, which is u sin theta. The acceleration along the x-axis is 0, acceleration along the y-axis is minus g, and then we can, to find out, let's say, the things like time of flight, for example, can we use something similar to what we used in our previous videos where we discussed the other types of projectiles? For time of flight t, can we say that when the projectile reaches the final position P on the ground, its y directional displacement is minus h? We know this h, right? The height from which the projectile was projected. So can we just put y, the y directional displacement, as minus h in the equation that connects the y directional displacement and the time, which is the second equation of motion? So in the equation y is equal to uyt plus half ayt squared, if we just substitute y is equal to minus h, we shall get minus h is equal to uy is u sin theta t plus ay is minus g. So, this will become minus g into t squared. See that what we are getting here is a quadratic equation in t. Knowing all the values here from the question in hand, we can substitute them and then solve this equation. We shall not be solving it further from here. As we do the questions in hand, we can directly substitute the values and solve them. Okay. Also, how to find out the horizontal range here? Our horizontal range, we can use the same method as we discussed in a standard projectile previously. We can just put t is equal to capital T in the equation that gives us the x directional displacement. X is equal to ux into t, because we know ax is 0. The second equation of motion s is equal to ut plus half at squared along the x axis will be only ux into t, and then we can substitute the values. So, u cos theta into capital T, we need to substitute here to get the value of x, and the x directional displacement then will be nothing but r, the horizontal range, right. So, this is how we can find out the horizontal range also. Now, how to find out the height of this projectile? If we look at this projectile carefully, it is like a standard projectile only, right, projected from the point O. So, as it reaches to the topmost point over here where its y directional velocity goes to 0, can we say that its height from that level from where it was projected, this height is already known to us, let us call it h dash. We know the formula for maximum height of a standard projectile, right, and here in this particular case, the maximum height from the ground will be nothing but h dash plus the h, the height from which the projectile was projected, right. So, we can simply say that in this particular case, maximum height reached by the projectile will be nothing but h dash plus h, where h dash is our usual maximum height, u squared sine squared theta by 2g, plus capital H is given in the question already, the height from which the projectile is projected, right. So, this is how we can work through a normal, a general projectile which is fired from a certain height, and we can get our values using the same 3 equations of motion, any one of those, whichever works for us. Let us look at a example just to understand this more confidently. The example is, there is a body which is projected from a height of 20 meters from the ground, and it is projected with an initial velocity of 10 meters per second, such that the initial velocity vector makes an angle of 30 degrees with the horizontal. So, u is 10 meters per second and angle of projection theta is 30, and as the projectile falls down to the ground, we are supposed to find out, number 1, the time of flight, capital T, and number 2, the velocity of the projectile as it reaches the ground. So, velocity at capital T at the final time when it hits the ground at that point. So, can we use the same basic equations? Can we say that for the time of flight, we can put y is equal to minus 20 meters, considering this point as the origin. We say that when the projectile reaches down at the point P, its y directional displacement is minus 20, and if we just put this in y is equal to uyt plus half ayt squared, right. So, what all do we have here? We have y is minus 20, uy, which will be u sine 30, substituting the values will be 10 into sine 30 is 1 by 2, that is 5 meters per second, and acceleration along the y direction we know is minus g, which will be minus 10 meter per second squared. We can substitute all these values over here to get minus 20 is equal to 5t minus half into 10 t squared, which when we solve will give us minus 20 is equal to 5t minus 5t squared, right. So, what we are getting is what we expected, a quadratic in t. Let us simplify it. We can take a 5 common throughout and can take this term, these two terms on the left hand side, so that we get t squared minus t minus 4 is equal to 0. This is the quadratic equation that we are supposed to solve. We can use the determinant method to find out the value of t. T is equal to minus b, which in this case will be plus 1, plus minus square root of b squared minus 4a and c, right. So, this is what we will get inside the square root divided by 2a, a is 1 here. So, this is what we are getting. See that this expression will give us two values of t, 1 plus, and within the square root we will have 1 plus 16, that is root 17 divided by 2, this is one root, and the other root with a minus sign, 1 minus root 17 by 2. Out of the two roots or two values of t that we are getting, which one should we take and which one should we discard? Understand that t can never take negative values, right. So, we discard this negative value root that we are getting here to take this particular value as the value of t, right. So, 1 plus root 17 by 2 then becomes the time of flight, capital T. Once we have obtained the time of flight, now we can find out the velocity at that time by using the same basic equations for finding out v, the final velocity, when u and t are given to us, right. So, for the second part of the question, velocity vector v, which can in general be written as vx I cap plus vy j cap, we can find out vx and vy separately. Vx will be ux plus ax into t from the first equation of motion, which in this particular case will be u cos 30 plus 0, ax is 0, right. So, 10 into cos 30, which is root 3 by 2, 5 root 3 meter per second will be the velocity along the x axis, whereas the velocity along the y axis will be uy plus ay into t, that is u sin 30 minus gy, that is 10 times. Now, in what time are we supposed to find out this velocity? At the final time. So, we substitute this value of t over here. So, it will be 1 plus root 17 divided by 2, right. We can simplify this now. U is 10, sin 30 is 1 by 2 minus, see that we will have some values cancelled out over here. So, we will have 5 into 1 plus root 17. This is also a 5. So, we can open up the bracket now, 5 minus root 17, right, and then that will be equal to minus root 17 into 5, there is a 5 as well over here, into 5 meters per second. So, this is the velocity along the y direction, right, at a time t. So, what we can do now is we can write the final velocity as the Vx, which is 5 root 3 I cap, plus the Vy, which is minus 5 root 17 j cap. This becomes the final velocity vector.